Let's get started. Hi, I'm Andrew Myers, and I'm going to be talking about security type languages. So I thought I'd start by just talking for a few minutes about why where does security come into this? Right? We're here for programming languages. What on earth do programming languages have to do with security? So we all know that computer security is a big problem, but is it a language problem? So historically, I think it's pretty clear that programming languages have at least contributed to the problem of computer security, if not solved it. So if you think about unsafe languages like C or C++, which are so prevalent, not the only ones, but probably responsible for a lot of the problems. These languages have specifications which don't nail down all the behavior. So you have undefined behavior. If you look at the spec for these languages, you'll see that there are more than 100 places in the spec where it says that the behavior is undefined. And so what that means is that the implementation is allowed to do whatever it wants. So this is the famous catch-on-fire semantics. If your computer catches on fire when you dereference a bad pointer, don't complain. There's no promise that wouldn't happen. So what undefined behavior then leads to is the ability for an attacker to exploit the undefined behavior and cause that undefined behavior to be something like starting up a new shell on your computer or running some arbitrary code. So that's been a big source of problems. And so that suggests that at a minimum, we ought to be trying to avoid using languages with undefined behavior. We ought to be thinking about the semantics of languages and using languages that give us strong semantics. And that's all good. And so what I'm going to actually be arguing, though, is that it's not enough. So I'm going to assume that we have already moved on to a new, the new world we should have moved on to 25 years ago, when we already had type-safe programming languages with memory management and garbage collection, all that good stuff. So rather than trying to patch C for the last 25 years, I think we should have just tried to really move to new languages. But even if we did that, we still would not be out of the woods. We would still have security problems. So I think what a lot of people have thought is, well, if we could just switch to a language with strong typing, and heck, let's ask for everything. Let's ask for really expressive dependent types, so that we can capture specifications directly in the type system, and then we're going to prove the heck out of everything. We're going to have a sound type system where we can express correctness of our software, and all the software we build is correct. Then we're going to be in good shape, right? That would be the hope. So I'm going to argue that this is not enough. At least not with the kinds of notions of correctness that people normally use when they're thinking about building computing systems. So as an example of that, let's talk about the recent Meltdown attack. I think it's kind of funny or disturbing that all of these attacks get branded. I think it's like, if the medical profession worked the way that the security guys did, then we'd have like Ebola plus, Okay, so this is an attack which has really caused a lot of problems for the people who provide cloud computing infrastructure. And the reason is that it actually violates a lot of the ways that we think about correctness and security. So let me try to write down a little piece of pseudocode. It's actually an attack that's done at a low level, but you can actually exercise it in some programming languages from high-level code. So here's roughly what it does. You have some code that's running, and I'm going to use some kind of equal opportunity pseudocode that is not like any real programming language, so everybody's equally confused. So we have some code running with some kind of exception handler for invalid memory references. And we have some secret we'd like to protect. Or actually, we're the attacker now, so we want to get it. So this secret is actually, let's say, some information in the operating system kernel. Right? The kernel is our defense on most computing systems, and it's something like, say, people's passwords, which happen to be stored in clear text at some moment, or other information that we want to keep secret. So we store that in a variable, and the idea is that we're going to be running this in user code, so this will generate an exception. But because of the semantics of hardware, hardware is trying to run really fast. That exception doesn't get delivered right away. That exception actually is delayed by potentially quite a few cycles. And so the program will actually keep chugging ahead doing stuff. And only later, when the exception is hit, will the hardware roll back the state, roll back the architectural state to where it was when the exception was generated. So you won't see any effects of all the stuff that happened later. This is the problem of speculation. But the processor will keep chugging along. And so then what we do is we use that period of time to do some more stuff. So what we'll do is we'll index into an array using the value I that we read out of memory. And so what this will do is it will load an address into the cache. So I said that, so the processor has two different kinds of state. It has so-called architectural state, which is the stuff that you see in the instruction set reference manual. So things like the contents of registers. And then it has microarchitectural state, which is stuff that's there to speed up execution. But the reference manual doesn't really make any promises about what's going to happen with it. It's just there to make things faster. So things like the cache, branch prediction, TLBs to some extent, various state in the architecture, in the implementation is microarchitectural, and the processor doesn't promise to roll that stuff back. So it's not going to preserve. Now, from the standpoint of the person watching this program run, they can't really tell that the rollback happened or didn't happen, except that it affects how fast things run. Okay, so what's going to happen then is this address will be loaded into cache. Then we'll get the exception. So I'll represent that as a try catch. Okay, and then what's happened is we've actually had a side effect on the cache. Microarchitectural state, not supposed to matter, but it has been changed. And so now we can observe that side effect by running a loop from 0 up to the maximum possible value of I. And we'll do some stuff here to time the access to M sub j. Okay, and in doing so now what we'll do is we'll loop through and we'll see one of those values of M sub j runs fast. It's the one that we happen to fetch right here into cache. And so we learn what the value of I was. But that was exactly the thing we were trying to prevent people from learning, right? So this attack, which is running in regular old user space, is supposed that the kernel is supposed to be protected from, is going in, reading out kernel memory. So we've just completely broken the fundamental protection that the kernel is supposed to be providing. Right? The kernel is supposed to be providing memory protection. You're not supposed to be able to read the kernel. Here we are, we're reading it. Okay. So what we're seeing here is OS read protection is broken, and this has caused a lot of consternation. And lots of people who were formerly using cloud computing to do various tasks have asked for levels of service from their cloud computing providers where they get much more isolation. They get the whole machine to them, stronger promises, and so like the new trend in cloud computing is that you get bare metal virtualization, which means basically you just rent a machine. So the whole dream that you'd be able to kind of just have your things run anywhere and things would move around, well, that's kind of broken. Okay, so of course it's not just Meltdown. In fact, this is emblematic of a whole series of things. Since Meltdown has come out, we've seen Meltdown, and then Spectre around the same time, and then people have been applying the same kinds of techniques to things like SGX, which are supposed to provide stronger hardware, and then there's a new version of that as well. And so this has been an ongoing thing. People realize, there's this problem where we can use the time to access microarchitectural state to learn things we weren't supposed to learn. And in fact, there are also purely software level timing attacks as well. So this is an example of a timing attack because we're using the time that it takes to do something to learn information we shouldn't. So, for example, there is an attack where you can read the pixels out of browser windows that you're not supposed to be able to read by timing how long graphics operations take. So it turns out that browsers try to accelerate how long it takes to do certain operations. They're rendering things onto your screen. There's a kind of slow path that you might have to follow in the worst case, but very often people are rendering things in a way that lets you accelerate. But it depends on the pixels that are actually on the screen. And so the browsers will try to follow this fast path. So that allows you to learn what the pixels are in windows that you're not supposed to be able to look at. So then you can read out information that is on on a different window in the browser. Okay, so that's so what's happened is people have realized, it's not just that there's Meltdown and Spectre, there's a whole class of attacks here. And all the people who do attacks are very excited. Okay. So what happened when Meltdown came out? So Intel was one of the companies affected by this. I mean, mostly Intel was affected by Meltdown, and pretty much everybody's affected by Spectre, everybody who has a modern processor with speculation. So what was Intel's response to this? Well, they said, this is not a bug. And that sort of sounds ridiculous. But I would argue they were correct. They never promised that this wouldn't happen. They gave us all a spec. They said, here's what the behavior is. And the implementation is correct as long as it follows this spec. And by any normal interpretation of what it means to follow the spec, they satisfied it. Okay? So let me try to elaborate on that a little bit. So what does it mean for the system to be secure? So normally, we have some kind of specification. We have a non-deterministic specification. You might say, my specifications are all deterministic. But they aren't, because your specifications don't talk about certain things that you don't want to have to talk about and shouldn't have to talk about, like exactly how many clock cycles it'll take for your functions to execute, or how many joules of energy will be required to compute it. Right? So there's a lot of stuff you don't want to have to write down in your spec. And so then, so correctness says the implementation should refine the spec. Right? The behavior that the implementation delivers should be one of the behaviors allowed by the spec. And if that's true, then we're okay. Or so we think. Okay? So in particular, if you look at the processor specifications, the processor spec doesn't say how long it takes. to do various operations. So, for example, reading from memory. And you wouldn't want it to say that, because if you did, then everything would break the minute you release a new version of the processor. Or even if you put a different memory, connected up different memory chips to the processor, which took longer. The processor doesn't try to nail this down because you can't have a processor family that lives for 50 years with evolution and have that kind of stuff nailed down. So we have to have flexibility in our specs. Okay? So the problem then is that these timing attacks, like Meltdown and Spectre, they exploit this non-determinism, and they do it by creating a correlation between things that are secret and these non-deterministic choices, like time. So the way that we normally think about correctness of computer systems doesn't allow us to talk about correlation. Because to talk about correlation, we have to talk about different possible alternative runs of the system. Okay? So this notion of refinement is something where we look at one run of the system at a time. We look at one trace of the system, and we say, is that trace one of the allowed traces? One of the traces that is... If you want to talk about correlation, it's not enough to look at single traces. We need to look at multiple traces and understand whether they introduce one of these bad correlations. Okay? All right. So what that tells us is we need a more expressive specification. Right? We need a better way of saying what it is that we wanted from the system, and we need better tools for checking whether the code that we write agrees with that specification. Okay, so what kind of specification would we want? So people have actually noticed the problem of timing channels for a long time, actually. It goes back even to at least the mid 80s, and I think even in the 70s people noticed that this was an issue, and so they started thinking about what it would take to talk about the correctness of computer systems, so the security of computer systems, and the kind of specifications that they came up with were specs talk about information. Which corresponds to this notion of correlation that I just mentioned. By the way, please let me know if I'm writing too small. I'm pretty sure I did a couple times there. I don't know how to signal it. Maybe a pinch to zoom gesture or something. But okay, so we need specs that can talk not just about the regular notions of correctness that we already have. We still need those, but also can talk about information flow. So, for example, we'd like to be able to say, more formally than this, that something like the contents of inaccessible memory do not affect the execution time of some piece of code. Right, that would be a spec that would let us feel confident that we don't have these kinds of vulnerabilities I was just talking about. Okay, so we need to actually nail down what does that really mean. This does not affect stuff. But that's the kind of spec that we would like to be able to capture. And then, of course, we need a way to enforce these kinds of specs. So what I'm going to be talking about in this series of talks is about these two things. So I'm going to talk about how we can specify security in a way that lets us capture information flow. And then I'm going to, which is a semantic question. And then I'm also going to be talking about how to enforce them, in particular by using type systems. So using security type languages that talk about information flow. So when I use the term security type language, what I really mean is something more general than the main topic here, which is a language where the type system is helping you reason about security and lets you express security policies in the type system. But to me, one of the most interesting kinds of security type languages is one where the security types talk about information flow. And so that's what I'm going to focus on. You can also have a security type language which reasons about capabilities. For example, there's a nice paper by Anita Jones and Barbara Liskov that showed this all the way back in '78. Okay. So, so let me give you a little, so let me just pause for a second here. Any questions? Yeah. Oh, capabilities. Yeah, it's Jones and Liskov. And it's 78. I think it's CACM, but I'm not sure. Sorry, it's been a while. Actually, this is a funny story. This paper actually gets the right rules for subtyping, contravariance and covariance. It's the first paper I know of to do it. So Butler Lamson at some point told me, oh, that was the paper where I learned about that. And it's like several years before Luca Cardelli's paper. Okay. Okay, so let me give you a little bit of history here, and try to introduce the main concepts. This has been a information flow, abbreviated as info flow, save marker, is something that people have been thinking about for a long time. I think the first paper that really clearly articulates it for me is a paper by Lamson in 1971. He wrote a paper called A Note on the Confinement Problem. So, as you know, terminology always changes over time. So originally people talked about it as the confinement problem, the problem of confining information. Still a good read. I recommend reading it. Butler is an amazing writer. So what he identified was this problem that information could leak out of systems, and that the conventional notions, the conventional mechanisms for preventing information leakage were actually not adequate. And so he gave lots of examples of smuggling information out through covert channels. So a covert channel here is so a channel is a means of transmitting information. A covert channel is a channel which was not intended to be used to transmit information. So these timing channels we're talking about are definitely in the category of covert channels. So subsequently, the term side channel has gotten a lot of use. So, and there's some difference in the way that people use these terms. So these timing channels are also, some of them are also side channels. So the idea of a side channel is that it's a channel where you don't have an active adversary, in some sense, trying to communicate information through the covert channel. So, but it's a tricky distinction. So the idea is, some people consider it to be a covert channel only if you imagine you have two computer systems, and one of them is running some code that the adversary has seriously compromised, and is trying to exfiltrate information to the other, and then using some channel like this to accomplish that. I think according to Lamson's original definition, covert channel encompasses all of these things. All right. So then one of the early and influential attempts to describe a mechanism for preventing this to prevent covert channels was a paper by Bell and LaPadula in 76. And they introduced the idea that you could have a computing system with various different security levels. So you could think it could be something just like user space and kernel space. Those would be two security levels. Or since this was done in a more military context, they would talk about having things like confidential, public, confidential, secret, top secret. That's a classic set of security levels that actually gets used in the. So the idea here then is certain information flows are allowed. So you can have information flowing from the public level to the confidential level, and that's okay. But if you have a flow going the other direction, that's not okay. And so you'd like to prevent that. And the insight was you could do that by controlling how processes in the system did reading and writing. So their rule was that they said there's no read up. That is, you can't, if you have a public level process, it can't read from information from a confidential process. And so that seems pretty, unquestionable. More controversially, they also said there was no write down. So what this says is the kernel, if you like, is not allowed to write into user processes. And so that, if the kernel cannot write any information into a user process memory, then you're in good shape because it can't leak its own secrets. Of course, that's super restrictive, right? The kernel actually needs to be able to write into user processes in order to give user processes results. So as an actual mechanism for enforcing security, this ran into a lot of practical problems, which I will address. So programming languages come into the picture with the work of Dorothy Denning and Peter Denning. So Dorothy Denning, in 1977, wrote a paper called A Lattice Model of Secure Information Flow. And what she observed was that the mathematical structure of lattices is a really nice way to describe this kind of system. So what happened was that after Bell and LaPadula wrote this paper, then various people said, well, this is pretty restrictive. We want to be able to say things. We want to have more fine-grained policies about who can read what. They started coming up with all kinds of policy languages, so-called multi-level security. And so Dorothy Denning said, well, actually, these are all just instances of lattices, and we should just be thinking about lattices instead. So the idea was that the policies here form a lattice. So in this lattice, we have an ordering which expresses what is the allowed secure information flow. So I'll write that as a square less than or equal sign. So we could say public is allowed to flow to confidential. To secret. And the nice thing about the lattice formalism is that then you can capture other things. For example, you can capture multi-level security policies. So you could have more complicated ways of labeling the information. You could say, I'm going to label this information as being secret and also about the nuclear topic. And that is allowed to flow to a place where it is stored with, say, the label secret, and potentially talking about both nuclear information and okay, since all of this was done in the military context, all the standard examples are kind of like this. I should probably come up with like Facebook versions of this or something. Close friends and okay. So that was great because now we kind of cleared away a lot of the clutter. And then a really cool paper was by Dorothy and Peter Denning working together in '78. And their paper is called Certification of Programs for Secure Information Flow. So this is really the great idea. So the idea was they would use static analysis on programs to verify that all policies. Right? And so they described it as more of a static analysis. But static analyses can be turned into type systems. What I do now is show you how to take the analysis that they defined and turn it into a type system. Before I do that, I just want to mention one other really important paper. So this is by Biba in '77. And what he observed was all of this stuff that we've been talking about so far has been about keeping secret information from leaking. Right? We've been talking about information flows are bad if they cause secrets to leak. Going to not be kept secret anymore. What he observed was actually we can also think about information flow affecting the integrity of information as well. So integrity of information is something we can reason about in terms of flow. So what does that mean? So the idea is some information is more trusted than other information. The trusted information has high integrity. The untrusted information low. And we can use the same kind of lattice reasoning that Dorothy Denning introduced to talk about that. So we can trusted information. Okay, I need more space here somewhere. Sorry, bad board management here. But trusted information is something that's allowed to flow to untrusted information. So the same kind of lattice reasoning makes sense here as well. If we can prevent the untrusted information from affecting the trusted information, then we'll, then we'll be more secure. Right. Now, you notice that there's something kind of, which is here when we were talking about confidentiality, the strong policy was on the right-hand side of the inequality, and here the stronger policy, in some sense, is on the left-hand side. So there's a duality here between confidentiality and integrity. And that duality is, in some sense, the thing that makes security hard, or one of the things that fundamentally makes it hard. Okay, there were a couple of questions lurking back there.
The last thought, I didn't catch the author's name.
Biba? Okay, good. Other questions? Okay.
What about when this is all creating the internet? So were they just worried about internal network attacks, basically?
Well, networks existed.
Yeah.
The internet predates the web, but these are forward-looking people. So they were definitely thinking about computer. If you read the note on the confinement problem, Butler Lamson's definitely thinking about network computer systems. Yep.
Yeah, for the static analysis, like for finding the security vulnerabilities, do you use something like type exceptions, like in Java?
Let me show you a type system, which I think will answer your question. Okay. So what I'm going to do is take I'm going to take the imp programming language. You guys know what that is? It's a while language. And let's add a security type system to it. Okay, so just to remind you, the syntax of imp is that we have a bunch of arithmetic expressions which include a bunch of operations on arithmetic expressions. We have Boolean expressions. With Boolean operators and relational operators on arithmetic expressions. And then what I'm really going to be focusing on here is commands. So commands are just skip, which does nothing, assignments, sequential composition, if, and while. Okay. So I'm not going to bother to write down the operational semantics for this, but at some point I'm going to start using an operational semantics for it. And please just ask questions if you need clarification. Okay. So now what we would like to do is write a type system that will prevent us from writing bad code. That is, leaks information. Now, right now, we don't really have much of a security. So let's add some ability to talk about security. So let's assume that script L is a lattice. And so it has a bottom element. Which you can think of as being public, at least if we're talking about confidentiality. Okay, so the idea now is that imp has variables. We're going to attach to every variable a policy for the kinds of information it's allowed to contain. So let's assume that we have an environment gamma, which will be a mapping from the various variables to elements of this lattice. And this gamma is just going to be kind of a global thing, so I won't even write it down in the rules. It's not going to change. Okay. So we're going to have the following kind of judgments in our type system. We'll have a judgment that tells us the label. Okay, I guess I will use a script lowercase l to denote some arbitrary element of the lattice. Okay, so we'll have a judgment that tells us what the label of an arithmetic expression is. We'll have a judgment that tells us what the label of a Boolean expression is. And mostly what this, so I'm not even going to write these ones out because I want to just write out the rules for commands. But the basic idea is you look at all of the variables that are mentioned in A and B, and you take the least upper bound of the labels on all the variables that are mentioned in them. Okay, and we could define it as a bunch of proof rules too. It's not that exciting. Okay. Oh, maybe I will write them down. All right, fine. Here are a couple. So numeric constants, well known, throughout this universe and every other universe. So a truth value, same kind of thing. And what if we have a variable, x? Well, we'll just look that up in the environment. Okay? And how about, just to pick another case, what about taking an arithmetic operation over two things? So we would like to say we have some A1 plus A2, or minus, or times, or whatever. What should the label of that be? Well, let's suppose that we've proved these guys have labels L1 and L2. Well, the label is just going to be the least upper bound, which I'll write as a square union. Okay. So this is right. So this is also known as the join. Okay. So now let's think about commands. Something interesting happens with commands, and that is we need to know what can influence control flow. And to see that, let me show you a little program which only assigns constants. So imagine that I have a program where I assign some variable pub to be true. So pub is going to be a bottom variable. And then I'm going to have another variable secret, which is not bottom. Okay, let's just suppose there's a top label. Really, really secret. And we'll test whether secret is true or not. And let's not assign pub to true, let's assign it to false. And in here, we will assign pub to the other extremely public value true. Right? So we're only assigning, the only thing we do in this program is we assign constant values to public variables, which sort of looks like it's harmless. But you can see that this is absolutely equivalent to doing pub get secret. Right? Modulo time. This is going to behave exactly the same way. So that tells us that whatever checking rules that we come up with commands, they'd better treat this thing as though it's like this thing down here. Okay, so so what's happening here is that we have what's called an implicit flow. So it's a flow that happens because some effect is on sensitive information. And so we need our type system to prevent us from having implicit flows. So the judgment that we'll use then is a judgment that talks about influences. So I'm going to introduce another label, which I'll call PC. PC here stands for program counter. So you can think of this as a kind of pseudo variable, like the program counter is a pseudo variable that's changing as the program runs. And we're interested in influenced that pseudo variable. What does influence ends up in the execution? Okay. So our judgment is going to say this command C is secure if run in a context where the program counter at the beginning of that command is the label PC. Right? So this thing is just going to be one of our labels.
Wait, sorry, can you just say that again?
So this program counter is going to be a label. It's going to be one of these elements of the lattice script L. Okay? Great. I guess I shouldn't have erased that, should I? You guys already know all this? All right, I'll just go over here. Okay. So let's try to write down some rules. So no surprise, skip, we'll consider that to be secure in any environment. What about an assignment? When should an assignment be secure? So an assignment, so first of all, we're going to assume that we know what the label of A is. So clearly, we don't want the value A to flow into X if A is something that's more secret than what X can store, right? So we require that the label of L has to flow into the label of X. And the kicker then is, we'll add another premise. We'll say, also, the fact that we're assigning into X at all is dependent on whether we ran this code at all, and the PC label tells us that. So PC needs to flow to gamma of X. Okay? And we could rewrite this with a join, L join PC flows to gamma of X. That would be equivalent. So the key thing then is this is going to catch implicit flows. So if you think about, well, okay, maybe I need to show you one more rule before I can really make that absolutely clear. So what did we use in our little example here? We had assignment, we had if. Okay, so what happens with if? So we're typing if in a context PC. We can give the Boolean condition a label L. Clearly we need to check that C1 and C2 are secure. But what should we use as the program counter label? Okay, I hear a vote for L. I hear a vote for L join PC. So PC doesn't get involved in the checking of B. So if we only use L, then we'll be forgetting the fact that we were influenced by something outside of the if itself. So L join PC is the correct choice. Okay, great. Yeah.
Is it correct that PC keeps track of the implicit flow?
Yes, PC is keeping track of the implicit flows, exactly. And so we need to keep propagating it to the expressions, subcommands. That's exactly right. Okay, so let's see, what have we not covered yet? We didn't get sequential composition, we didn't get while. And there's actually some interesting choices embodied in those. So if we want to check a sequential composition, then we don't learn anything from the fact that we got to the beginning of C2 that we didn't know from getting to the beginning of C1, assuming that C1 finishes. So, which we don't actually know. So I'm going to make a deliberate choice here that we're going to ignore the possibility of information leaking through non-termination. Okay? And so with that choice, our type system is simple. We can say C1 type checks in this program counter, and then we know that we have to end up at C2, so we use the same exact program counter. Okay? And then finally, I can write a rule for while. And the same reasoning applies here. So we'll have B is some label L. The fact that we execute C, this is a lot like the if case, right? So the fact that we execute C depends on the Boolean. So we just take L, join PC, and check C. Okay, so now if we go back and look at our example up there, which somehow I wrote in a Java-like syntax, but think about what would happen there with the checking of the pub gets true assignment, right? So in our example, what we're going to be seeing, since pub gets true is executed as the consequent of an if command, that means that the program counter is the label of secret, which we said was top. So the PC that we're going to be checking the pub gets true will be the top label. And so the thing that we're going to be trying to prove in our type checker is this statement, which won't work because top will not flow to the label of pub. Right? Okay, so that just shows that we're able to deal with the implicit flow problem that I talked about. Okay. So, any questions? Yeah.
How big of an assumption is the non-termination, that we're not leaking anything through non-termination?
So this is really a judgment call. It kind of it depends on the system you're trying to apply this to. Now notice that if you can prove, which often you can, then you get the full security guarantee. So you can think of this as a way of factoring the problem into two problems. One is proving that you don't have information flow if you don't have non-termination, and then proving that you don't have non-termination. So and there's been progress on proving non-termination as well. So I think that's actually a reasonable way to go. Yep.
How would you formally define the different levels within the lattice in your system? Like, obviously we know public doesn't flow to secret because we say that, but we don't say it super formally at any point.
Right. Well, this is really just a policy language right now, and I haven't given it a semantics.
Okay.
So what I want to do next is give it a semantics. But different policy languages may allow us to connect to other things that are happening in the system. For example, if our lattice lets us talk about principles in the system or host machines in the system in a network system, then we might be able to connect it to what kinds of failures are allowed on those host machines, for example. Yep.
Can you think about the effectiveness rule sort of like a localized write-down rule? Because instead of processes talking, we're just saying like, when in this if statement, we're in a supervised or we're like privileged mode.
Yep.
Yeah,
that's a very good insight. Right. We're trying to prevent writing into a low thing in a high context. That's right. Okay, great. So let's talk a little bit about the semantics now. So you might be wondering, like, okay, this was all kind of fun, but what did we actually achieve? Like, what did we prove about the system? So let me return to historical mode for a moment. There's a very nice, another very important paper by Gauguin and Messiger from 1982. Introduces this idea of non-interference. Okay, one of my pet peeves is people writing a hyphen here, so don't do that. Okay, so what they tried to do was to pin down what it means for a computing system, in their case a deterministic computing system, to not leak information. And so their idea was to compare hypothetical executions. So we think of the system, we're trying to come up with a kind of extensional description of security here. So our system, and the system has different kinds of inputs coming in and different inputs leaving. So we'll just imagine we have a 2-point lattice where we have high security things and low security things. In general, we can just take the lattice and we can partition it into kind of a high security region and a low security region. So we're not going to lose any generality here. But just for simplicity, let's think about there's 2 kinds of information. And then we have high information going into the black box and low information going into the black box. And at the output side, we have high information coming out and low information coming out. So we'll call that prime and L prime. Okay, now just by looking at one execution of this thing, we can't tell whether we're leaking information. So their idea was, okay, let's imagine that we have a second black box, and we're going to feed it different information. So we'll call this one H1, this one will be H2, H1 prime, but we'll keep the low information the same. Right? So only high information, only the secret stuff changes on the input. And on the output, it's okay if the high information changes as a result. If it doesn't, then we have to wonder what on earth the high information was being used for in the first place. But we want to see exactly the same low information coming out. If the low information changed as a result of changing high inputs, that means that an observer of this system from the outside can tell that they learned something about the high inputs. And so if you want to say that you're not learning anything about the high inputs, you can't allow that. So another way of viewing this is that we can think of this as an equivalence relation. So there's some kind of low equivalence relation that says the inputs to this thing are indistinguishable to an adversary who's only allowed to see public information. Right? So this low equivalence relation only looks at the low part. And what non-interference is saying is, execution preserves the low equivalence relation. It's saying, if you start out low equivalent, you run the program, the results you get are also low equivalent. So you didn't learn anything in the process. Okay? I think there was a question, but maybe...
Is this related to like the idea behind differential privacy?
Yes. Yes, definitely. She asked if it was related to differential privacy. So that's a probabilistic statement, but it's definitely a closely related idea, because that has to do with indistinguishability of probability distributions. And so we're definitely talking about indistinguishability here. But we need a more nuanced notion of indistinguishability there. Yep?
So H1 and H2 are hidden?
The idea is that, yes, they're hidden to the particular observer we're worried about. So we're worried about an observer who can only see public things. And we're trying to keep them from learning secret things. Right? All right, great. So if you have a diagram like this, what this is telling us is H doesn't affect L. Right? We don't have an information flow from H to L. And you'll notice that this is now, we're actually talking about 2 executions. Right? We're talking about, in fact, we're actually executions that satisfy some criterion. So rather than, I mentioned at the beginning that we needed a more expressive way of talking about correctness, one that didn't just let us, we're not looking at just one execution at a time, we're looking at multiple executions. So normal correctness would say, you look at all individual executions, they all obey the spec, you're good. Here we're saying, no, you have to look at all pairs of related executions. And in that case, you should expect that in all those executions, the outputs are also related. Okay, so we have a relational specification. All right. Okay, so let me try to formalize this a little bit more crisply. So let's suppose that we denote the of the system by S. And I'm going to include even the program that we're executing in this state S. And so what we'll say, we'll introduce some notion of indistinguishability to a low observer. We'll say that two states are indistinguishable if they are in relation. And so what we're trying to now do is preserve this indistinguishability. So I mentioned that we could have a 2-point lattice. In general, we could have a lattice where there's some region, which we'll call the low region, and then there's some region that's not low. And the idea is that our observer, who we can think of as our adversary, is going to see this whole region of the lattice. So there's some point here, I should put the L here, there's some point L, where you can think of as a point in the lattice, and everything below L in the lattice, I'm going to draw a lot of lattice diagrams like this, so hopefully this is intuitive. So everything that's below L in this lattice is something that the adversary can see. Okay? So you can think of it as these two states are indistinguishable if when we project them onto all the components of these states that are in the kind of the low region of this lattice, then they are equal to each other. Okay, but it doesn't have to be that way. So I'm trying to keep this pretty general. Okay, so now let's also talk about the behavior we get when we run the system. So in Gauguin and Messinger, they were thinking more about the kind of the final state of the system. But in general, we may want to talk about not just the final state, but maybe things that happen along the way, right? Their effects that the program is having. So in general, we may want to think about traces that are executed, or maybe distributions. So let's denote the behavior by using double brackets. So let's say that bracket S is the observable behavior from executing S. Okay? So that could be just a trace. It could be just the final state. It could be a set of traces. It could be a distribution over traces. It could be a lot of things, depending on how exciting you want your semantics to be and how faithful you want to be to some underlying system. So then what I will now do is introduce a notion of indistinguishable behaviors, which we're not going to really pin down what it is because we want to be generic. So we'll write S1 is indistinguishable. I'll use a double squiggle. So S1 is indistinguishable to an L level observer from S2 in its. And so I'll write it that way. Okay, so now we have a way of talking about what it means for the initial state configuration to be indistinguishable. We have a way of talking about what it means for the behaviors to be indistinguishable. So now I think we can write down non-interference formally. This is not, by the way that Gauguin and Messinger originally wrote it down. So you can think of it as a kind of updated and generalized version. So non-interference, the essence of it is that if you have two states that are indistinguishable, then the subsequent behaviors should also be indistinguishable. Okay? So that's just really just that diagram again, but we're writing it down formally. Okay, so now there's lots of room for making choices here. We didn't really say what the states are. We didn't really say what this relation is. We didn't really say what this relation is. And we didn't really say what the semantic brackets are doing. So by playing with all of those things, we can capture different notions of security and different assumptions about the system that we're trying to think about. So these relations that let us compare states and behaviors are really telling us what the adversary can do. They characterize the power of the adversary. And this is a really critical thing. Whenever you're thinking about security, you have to think about what are the powers of the adversary. If you assume if you say the adversary can do anything it wants to, then the game is already over. Right? You have no security. So the challenge is always to define the threat model, which is the powers that you allow the adversary to have, and then to say, do we have security with respect to that threat model? And then when you're actually trying to deploy a system, you try to make sure that the system is in accordance with that threat model. Right? The adversary really only has the powers that the threat model gave to them. And often that will mean adding extra mechanisms, maybe mechanisms outside of computers like locked doors and adequate salaries for security guards and other real-world things. Okay. So one of the key choices then here, which I've alluded to already, is whether we want these notions of indistinguishability to be sensitive to termination. So do we want a termination-sensitive notion of security or insensitive? So sometimes this is abbreviated as termination-sensitive non-interference versus termination-insensitive non-interference. So reasoning about termination is hard, so very often people use the termination-insensitive way of doing things. So how can we capture this termination sensitivity or insensitivity using these relations? So if we say we're termination insensitive, what we're saying is, in some sense, the adversary can't tell when you don't terminate. It's sort of like the adversary is never quite sure whether the program's just taking a long time, and he never comes to any conclusions when the program fails to complete yet. So for termination insensitive non-interference, what we'll do is we'll say that all behaviors are equivalent or indistinguishable from divergence. Okay, sorry, this is a bit of a overloading of terminology here. So this bottom is not a lattice label. This bottom represents denotational semantics, but that's the usual symbol for that. Too many lattices. So what that says then is, if you write something like this, while true, well, let's say, while secret do skip, that's a secure program. So, maybe a little disappointing. But as I said, you can take termination insensitive non-interference plus a termination proof, and that will give you termination sensitive sorry, take termination insensitive plus termination, that gives you termination sensitive non-interference. Okay. Another thing you might notice that channels before, right? Timing channels correspond to being able to observe execution steps, the number of execution steps. And so what that says is if we ignore timing channels, then we can write, sorry, if we don't ignore timing channels, then we might want to consider this program to be insecure. Right, here we have a program that spends more time uselessly skipping, maybe, depending on the implementation. So this is going to be secure under most of the definitions that we'd use if we have a notion of indistinguishability that doesn't take timing into account. Okay, so one particularly simple notion of indistinguishability so I've been talking here about the double squiggle equivalence. Where do we get the single squiggle equivalence from? Very often what we have is a state that we can partition into two parts, or partition around a particular label. So we could say, well, our state S is actually it comprises some high state S sub H and some low state S sub L. And then we'll say that one state S1 is low indistinguishable from S2 if the low part of S1 is equal to the low part of S2. Okay, notation's not too precise there, but I think you get the idea. Okay. Now actually we can, so far the policies I've been talking about are pretty coarse tomorrow, I guess. Okay. I thought it might be fun just to mention a few of the real systems that have attempted to instantiate this kind of approach. Just to give you the idea that it's not all completely untethered theory. So the first system that I know of that tried to implement static checking of information flow is a system called Spark Ada. So this was developed in the late 80s, early 90s. I think they're still working on it. It's actually it tries to do much more. It's a version of Ada with support for a theorem prover as well. But it also lets you talk about information flow, and it's based on the Denning and Denning paper very closely. Another system that I have been most closely associated with is a language called GIF. Actually, it was originally called JFlow, but then I got sued. Yeah, it was I forgot what it was. Somebody had trademarked, and anyway, it was easier just to change the name. So this is a paper from Popple 99, and so this is Java plus information flow. And this is actually a system you can still download and play with. Maybe I'll do a demo when I get a chance. Subsequent to that, languages were developed. So there's something called FlowCamel. So FlowCamel is developed by Francois Potier and others. Very cool system. Comes with really nice formal results. I don't think it's that usable for building software. I think they would admit that too. But it is really nice. And then there are other systems. There's something called Laminar, Paragon. Recent system, there's a system called Joanna, which by Gregor Snelting, which tries to do sort of what GIF is doing, but let you write your code just in regular old Java, and then uses program analysis rather than a system. There's a system out of the University of Washington called IFC, stands for, I guess, Information Flow Checker, which is a bit generic, but it's developed for web applications, and they were actually able to show one of the cooler results, pragmatic results in this space. They were able to show that when they checked web applications using their tool, that a red team of security professionals were unable to break any of the things that were allowed. So they actually had a red team writing web apps and inserting vulnerabilities, and they were able to catch all of the vulnerabilities that were inserted. So that's pretty cool. Okay, and more recently, my group has been looking at applying this kind of technique to hardware level side channels. So we've been looking at timing channels and thinking about how to prevent things like Meltdown. And so we've been taking this approach at the level of hardware description languages. So if you guys have ever used Verilog, that's a language that you use to write down hardware. So we have something called Sec Verilog, which is Verilog plus information flow types. So I plan to tell you a little bit about Sec Verilog on Thursday. Okay, good. I think I'm out of time. So I will stop here and save my GIF demo for tomorrow. Or, yeah, probably tomorrow. Good, thanks.